Okay, great. So our next speaker is Danqi Chen, who's an assistant professor at Princeton University, working on natural language processing and focusing on things like retrieval and long context stuff. So, thank you.
Okay, thank you, Len. Thanks everyone for joining. I'm excited to be here today. So I know the theme of the workshop today is on model architectures. So today my plan is to talk about two families of language models. One is the retrieval-augmented language models. Another is long context language models. The reason I put these two together is I've been actually working on both problems for quite some time. And honestly, I cannot decide which one I should talk about. So both seem to really fit today's topics pretty well. Another actual reason is that the more I work on both problems, I actually feel there is actually very natural connections between these two families of models that people might not be familiar with. So for this talk, my plan is to first tell you my current views of these two families of language models. Then I will talk about how to really train retrieval-augmented language models and long context language models separately. Actually, hopefully I will want to spend most of the time on the part 3 about how to train long context language models. The reason is because we more or less actually figure out some kind of open recipe for training long context language models. But for me and also many of you are sitting here who have been working on retrieval-augmented language models, so far we actually really haven't figured out the solution for how to train the retrieval-augmented models. Also, I want to mention, last time I came to Simon's was actually beginning of the academic year. Last time I was asked to give a talk on how to train language models. And I got so many questions, and I was only able to finish half my talk. So today I'll see how things go, but I really hope that I can at least get to the part 3 of this talk. Yeah. Okay, so let me start with some definitions, I believe. So let's start with what are long context models. This is actually very easy to understand. So long context language models are basically a family of language models that are capable of handling long context sizes. So this usually refers to long input tasks. For example, you want to put a book or several web pages in the context of language models for the models to parse. But more recently, this can be also referred to long output tasks. Especially with recent very popular long chain of thought models, they all actually have to rely on the long context language models to actually generate long and coherent thinking traces. Then there is this most important axis of long context models is actually the context size. So here's actually something I don't know if people are actually aware of. So when we start thinking about long context language models in early 2023, most of the models at that time really don't have a very long context size. For example, the Llama 1, Llama 2, or even the GPT-4 from OpenAI at the time really have only context size of 2,000, 4,000, 8,000 context tokens. But just 1 year passing, most of the frontier models today actually support at least 128,000 context window size. And the Gemini 1.5 Pro even supports up to 2 million context size. That's really, really incredible progress. So next, let's talk about retrieval-augmented language models. So my working definition of retrieval-augmented language models is that it's a family of language models that are actually inherently designed or trained to incorporate retrieval during inference. Even today, you probably know a lot of the modern language models that are trained in pretty standard ways. They're still very capable to call retrieval. So this here, I want to put slight emphasis here. This language model should be actually designed to incorporate retrieval during inference time. So next, let's talk about what is retrieval. So there are also two views here, right? So one view is actually we can just simply call a search engine API, like a Google or Bing. And this actually, you really don't need to care about what retrieval works. And this basically was viewed as one of the most important applications in tool use. So the second view is actually you actually need to build an embedding-based index. So here we need to train the encoders, save this index, and then we need to do some form of the nearest neighbor search in this vector database. So in case you are actually these days still I have students ask me why you actually even want to bother building this kind of embedding-based index for retrieval-augmented language models. So here is what I think. Definitely, if you can actually have this kind of in-house built-in retrieval index, it's actually much better for doing the reproducible open research. The second reason is actually this family of retrieval augmented language models. If you can actually train the retrieval, you can build the retrieval by yourself. It's actually still ways that you can actually do this kind of end-to-end training of the retrieval and language models. And even how to do retrieval is actually also a very important research problem that actually I personally have been working for many years at this point. The next question I want to talk about is how is actually retrieval is actually used in language model. And the most widely used or the naive way to use retrieval is really you just take the input query, you call the retrieval, and then you fetch some of the retrieval documents and put these retrieval documents back in the context size of the language models. So this is what people usually call RAG or retrieval-augmented generation. It's a very simple pipeline. Just put the retrieval documents back in the context. And there is another more advanced view of how to think about retrieval. It's actually this view of like doing the retrieval in a more interactive or like a multi-turn way. That you can actually let language models decide when you actually want to call retrieval, and what query exactly you want to call the retrieval, and how you're going to use this retrieval. So this is what people usually call as agentic search these days. For example, like OpenAI's deep research has been really like a big thing recently. So this is a very super popular paradigm, but I'm not going to talk too much today. Okay, so next question is why do we care about retrieval? I'm actually pretty sure that everyone knows that retrieval is pretty important for language models. Many of us must have used like search or like retrieval features of these language models. Even with like ChatGPT, there's like a search feature, or you can use like a Perplexity AI. Then you can definitely like, for example, actually the flight I took to Berkeley this time actually got delayed, and I asked Perplexity like, can you tell me whether this flight UA 1306 was on time the past week? It does actually a really good job. You will not really trust a language model to handle such queries if the language models don't have a retrieval building, right? Because you're just asking about the flight information in the past week. So there's clearly a lot of great things that retrieval can bring to us, such as factuality. Well, many of us should still believe that language model cannot really pack everything. There's still a lot of the long-tail knowledge. And another important thing is actually really this adaptivity and also freshness, because we cannot always continue training language models to make them keep up to date with the real-world knowledge. And the third benefit I want to emphasize here is actually attribution. If we get some output from language models, if we have the retrieval, at least we can know that where these outputs actually come from. And then you can go back and check a source to see whether the output is actually reliable or not. Finally, the last angle I want to talk about here is actually maybe not everyone knows here, is actually the angle of the efficiency. At least back to a few years ago, many of us actually believed that retrieval could be actually a really promising way of actually scaling the language models. So this actually is, there's a really one of my favorite paper coming from Google in 2022, 3 years ago, called Rachel. Actually, how many people here actually are familiar with the paper called Rachel? Actually, not too many. Yeah, I'm pretty sad. This is really one of my favorite papers back to a few years ago. So their really claim here is that at that time, the strongest model at the time was GPT-3. And their argument is that if you have a really large vector database, you can actually train a small language model to pair with this database to actually outperform the large language models. And they say like, with a 2 trillion token database, the Rachel actually obtains comparable performance to GPT-3, despite using only 25 times fewer parameters. So this seems to be really promising 3 years ago. But unfortunately, 3 years later, many people even don't remember this paper. And we haven't seen enough progress in this direction. And I will talk a little bit about what I think are actually the potential reasons. So next, I want to talk a little bit about attribution. So this has been actually a small turning point for my research as well. So in early 2023, we actually wrote a paper. So this paper is called Enabling Large Language Models to Generate Text with Citations. So this benchmark is called ELK. Essentially, the end-to-end automatic evaluation framework for large language model citation. And what this task is actually doing is, so basically the task for this task, you have like an input query. And we ask the system to actually, so we also provide the system actually a like predefined retrieval corpus. And the system needs to retrieve a set of passages from a given corpus, and then use these language models to generate a relevant output to this input query, and with actually the correct citations. So if you can see this input query with also like the language model output, you can see a lot of citation, like 1, 2, 3 in this like square brackets. That basically means that the language models need to figure out like which of the retrieval documents can actually support those generations and actually need to tag with the correct these kind of citations. So for the evaluation part, we actually need to evaluate both the correctness of the language model's output and also the citation quality. So the reason I brought up this paper, again, is almost 2 years now, is that we actually have learned quite a bit for solving this task. This is early 2023. And we are really trying to leverage some of the best language models at the time. Again, only support context size of like 4,000 to 8,000 context tokens. So the figure on the left is actually the evaluation on correctness. The figure on the right is actually on the evaluation on the citation quality. So we found like even we can put like 50 documents in this long context context size for the best language models at that time. The models actually struggle a lot with actually leveraging the information provided in these documents. For the correctness, so the green curve here is basically some retrieval record. That means how much information is actually already correct information is actually provided in the top K retrieval documents. But actually the correctness score has been actually decreasing basically after using like 15 to 20 documents. For the citation quality here is actually the performance decrease significantly. Basically from the beginning, the more documents you use, the worse the performance is. So this actually is measured on Llama 3, but at the time we only evaluated on Llama 1, Llama 2, and also GPT-4 models. So basically my student redid this figure. So really what's wrong with these language models? Again, this is early 2023. So we did have really good long context language models to really support like models to actually parse these kind of relevant documents and generate the correct outputs. And it could be also a problem that model is actually not able to do the instruction following pretty well because the citation quality, we believe that it actually really requires model to follow the instructions to do well on this task. Okay, so for me, at that point, it was very clear that we have to work on long context language models to support the RAG applications. So that's why we actually, in the past 2 years, we have spent a lot of time working on long context language models. So, but there's actually another really interesting discussion in the community. Go ahead.
Can I just ask really quickly?
Yep.
Last slide.
Yeah.
Your point here is not that RAG is broken; it's that if you find the documents, you can't.
We already find the documents because this is the green curve is serves as the upper bound.
I see. So the model is just failing to use the
documents. Yeah, exactly. Yes. Yeah. Yeah. Go ahead. Yeah.
Just not understand what this plot means. So you're putting 50 documents in the context; they're already there, and it fails to find. So there's a lot of documents and there's a question.
Yeah.
It fails to find. Can you explain?
Okay, so we basically enumerate the top K retrieval documents, put them in the context, let the model generate and cite for whatever output it generates. So we have some automatic metrics to give you a correctness score and a citation score. We found that actually the performance on both sides actually decreased a lot after 15 documents. For citation, it basically start to decrease immediately, based after 5 documents.
Is this also the case with the current founded models?
I have some results for the really the best model like Gemini Pro is not a problem for that, but that's really the old models. Yeah.
Does it matter that these 50 documents where the correct citation is located?
We don't control that. So it's basically we take the top K retrieval document according to some kind of retrieval scores, similarity scores.
When I'm needing long context, to what extent is it agreed that the right way to do it is to put the retrieved documents in the context window? Maybe you could have a compressed representation that you use directly, almost like a encoded.
Yeah, I agree. Yeah, a lot of people working on RAG, they are trying to figure out how to do another first step to parse the information before you put in. But here, but also this pipeline is actually very popular in the industry. That you have long context model, you just put everything here. Go ahead. Yeah.
Can you explain how should we interpret this retrieval recall upper bound at 50? Is it all the 50 documents are relevant at that point?
There is some nuance here. So the questions we pick in this benchmark, for example, ambiguous questions actually proposed by Sewang, you actually need to hit multiple answers. So that means that we want to check how many of these, what is the percentage of answers that are already included in the top K documents. Okay, let me move on. Yeah. Okay, so we believe that we need a long context language model to support RAG. But in the last year, there has been actually a lot of interesting discussion in the community. Like, given the long context language models have become so powerful, like they can support context size of like millions of tokens, can we actually even use long context language models to actually replace RAG? Let's say we just put so many of documents in the long context model to let the model figure out this. Especially with the frontier model like Gemini Pro, they seem to be doing really well. So there have been actually a lot of papers I put here. The first paper is actually from the GDM, from like people who work on Gemini. So they have been really asking this question: can we use long context language model to replace RAG? And there have been actually a lot of empirical studies on this topic as well. But actually, the conclusions actually also not so conclusive, because people have been starting different families of models and different context sizes. But as a figure, you can show here from the one of these papers, at least on the left. They basically show that with the frontier long context models, it actually seems that they already outperform the RAG in many of the settings. But still, RAG is actually much more significant than long context models, because RAG essentially already does the first step processing. So here are just some my current take on this problem. So I still believe that we cannot really pack everything in those sizes, even if long context models context size can grow up to millions of tokens, because this is still way significantly smaller than the basis of the retrieval corpus that we actually usually consider. But still, I think that if we have very good long context language models, they can actually lower the bar for building a very accurate retrieval. I personally care a lot about building retrievals. Just today, there's still a lot of retrieval questions we don't know how to answer. For example, coding, math, a lot of domains that we don't know how to build a good retrieval. But if we have a very good long context language models, maybe we don't need a very good retrieval. We just try to use long context language model to try to solve this. And the third aspect, I agree that RAG should be generally more efficient than long context language models. But there are also many people actually trying to really work on efficiency techniques for speeding up the inference process of long context language models. Actually, many of these techniques actually very closely related to actually how retrieval works. So this actually, there's a very interesting connection to think about there too. Okay, so this is the first part I want to talk about. And the second part I want to talk about is actually how to train retrieval-augmented language models. So later, I want to just spend 5 minutes talking about this part. This used to be really my favorite topics back to 2 years or 3 years ago. So actually, many people like Luke, Sevon, I think we guys here, we have been actually really working a lot on this problem. But I'm pretty sad that we haven't still made enough progress today. So given this workshop, future of language models, I feel I should at least tell you that what kind of problems we are thinking in space, and hopefully we can still see some breakthroughs in the next few years. But I'll be really quick about this part. So what I mean by retrieval-augmented language models here is that we really have this a very large database built in this model architecture. So there is a very large data store that you actually need to train the encoders and then encode every item in this data store with a vector representation. And when you do the standard language modeling, for example, you have a prompt that Princeton University was founded in, you actually have to first go through this data store, do the nearest neighbor search, and fetch the top K documents, and then combine this with the orange language model to actually help with making the next token predictions. So I list a few papers here. Actually, there are really a lot of very active explorations and really cool ideas back then. But one thing you can find here is actually all these papers actually were around 2022. So we actually haven't seen a lot of new papers coming out in the last 3 years. We even actually did a tutorial in 2023 with Sevon and other folks at ACO. And we really spent 3 hours talking about what kind of different architectures, different training methods we can actually use for training for building a retrieval-augmented language models. And that was really popular at the time 2 years ago. So here are some papers. I actually, at least in the previous slide, I already mentioned this paper, Google's Rachel paper. Actually, on the industry side, Meta also had a really big paper called Atlas, again in 2022. So even on the academia side, again, many of our research groups have been really thinking a lot about how to train such retrieval-augmented language models. Basically, how to do the end-to-end training together of the language models and the retrieval. Again, I list a paper from my group and also 2 papers actually from Luke's groups here. So why is the training retrieval-augmented language model so hard? So actually, the main bottleneck here is there's a language model, there's a data store. And then you need to backpropagate to both the language model and the data store. But as long as you actually need to update the parameters actually related to this for building this data store, then you have to actually basically like re-index this data store because the parameters have been changed, the encoder has been changed, you have to re-index this. And this could be actually extremely expensive. So you have to come up with some kind of clever ideas to actually work around this problem, to actually really enable this kind of joint training of data store and language model, essentially. Yeah.
So, but I thought the data store is converted to embedded.
Yes, but the encoders actually need to be trained together. That's the point. Yeah. And just give you some ideas. So at the time, again, 2-3 years ago, people come up with a lot of really interesting ideas, regardless of actually the model architectures, about how this kind of joint training can be done with the language model and the retrieval. You can train one part, and then freeze one part and train another part. Or you can do the vice versa. Or you can actually even think of something like asynchronous update, or doing something like in my group, we did something called in-batch approximation. Maybe not that important, but I just want to say that there are actually a lot of really interesting creative ideas we were thinking about to actually make this training work. Okay, so this is my last slide of this part is why is actually the progress in training retrieval-augmented language models actually has stalled in the last few years. Honestly, I don't have a very accurate answer. To be honest, I really think there are just not enough many people actually working in this space. We don't have a critical mass in the field actually working on these problems. And at the same time, there have been actually a lot of breakthrough happening in both in the community. So, for example, if I take the Rachel example, at that time, the largest language model was GPT-3, 175 billion. And they claim that they can use the 7 billion model to actually beat the GPT-3, 175 million. But today, actually, there have been a lot of breakthrough made in the small language models. Today, you can actually, with a 7 billion model, you can already do a lot of really great things. And also on the retrieval side, people do a lot of really exciting things about this kind of agentic search that I already mentioned. So just a lot of other things going on. I think we haven't really made enough progress. Because it's actually a pretty complex family of language models. So we have to really explore the model architectures and also the training methods. So it's still a lot of like a design space that we have to explore. But even these design choices have been not really fully decided at a small scale. So we haven't really got enough people to really try to figure out how to scale up such models. And I also think for this line of research, there has been actually really a significant barrier for the open source research because there is a very big data store that you actually have to experiment with. Even I have some students in my group who are very good at engineering, but there's just not many students who want to work on such problems. It involves a lot of engineering efforts. And also another big problem is there's a big component of this kind of models that actually the data store. So we have to think about how to create like open source data store. And actually, like also from Luke's groups, people, this is a paper from New York's 2024. People are still thinking about like how to create this kind of open source data store and think about what should be the scaling laws for scaling the retrieval and language models together. So there are still things going on, and I really hope that it's not an easy research problem, but I hope that still a lot of people be interested in these kind of problems and work on these problems together. Yeah.
Is there a scaling economy that do large models do better retrieval?
That part I'm even not sure, because for this is usually a very large data store, and people play with like a range of the small to medium-sized language models.
Fine, but in that range, is it true that larger models retrieve much better than?
I believe should be the case because better language models usually always lead to better retrieval. But I cannot be.
I would expect, but I'm just checking. Is that true?
I'm not sure if there is any empirical
In
thing.
some sense, a different way of thinking about it is, does retrieval still help large models? Which is a different question, but also kind of interesting because
whether they can find better.
And it does, actually, which is sort of interesting. And then this paper, we're scaling the size of the data store too. So bigger models, bigger data stores, things just get better. And so it's almost like another scaling dimension.
Yes.
And that's kind of cool, but it's really hard to do.
But even for the same data store, it gets better.
Yeah, you can take the original pre-training data for a model and put it in a data store and do RAG, and it will get better.
Go ahead.
I'm trying to think about how this section about training retrieval-augmented models squares with the fact that it seems like Perplexity and Gemini work pretty well. Is the thought here that they figured out something that we're also trying to figure out, or all this also applies to whatever they're doing?
So for for example, Perplexity or this kind of more like on the side of the agent behavior. So you train language models. You let the models figure out how to do the retrieval, but you don't care about how to train the language model for the retrieval. Here, the vision is still always like you have a retrieval that trained together with the language model. So that actually can benefit from the retrieval to actually make a small language model work better. Yeah.
So you're saying they're not even trying to do this whole paradigm?
I think we don't have enough work in that space. Yeah. Certainly, yeah.
Can you speak a bit about what you want these models to do that they're not doing? Like what skill do you hope them to learn and that you're not seeing them?
The goal here is to build a general purpose retrieval-augmented language models that can actually do like definitely all the factoid task, but also can do like reasoning, all these kind of general purpose tasks. So, but the hope is that with the help from the retrieval, small language models can actually do better. Yeah.
But where are they failing? Are they failing at the retrieval stage? Are they failing at the integration stage?
There are actually a lot of things that are actually really behind. For example, there are some studies showing that the generation quality has some issues because of the retrieval. And also, I also think another problem is the computer has moved so fast with the post-training. There isn't any post-training work done in this space, much. There is a work called instruct retrieval kind of thing from Amazon, I believe. But there just hasn't been enough work. If we think more about how to do the kind of post-training stage for these models, I do think these models will do much better. Yeah.
So the initial question is that, are you assuming that the better data source is not in the original training data, you try to make it better, or you think that some information missed by the original data? So what's the...
Okay, so first you can put things that are actually not in the pre-training data in the data store. That's really for the refreshness or the adaptation of these models. Second, you don't have to train on all the hope is that, let's say if you have like 10 trillion tokens, maybe you only need to train on a fraction of the training data and put the rest in the data store to actually reduce the cost of the pre-training.
So you're not argumenting some existing model?
Yeah, correct.
Are you or are you not? I'm not very familiar with that.
So say one more time, sorry. Augment.
Are you taking some existing model and try to do retrieval to enhance that, or you're really doing it together?
We really want to train these models from scratch. But if it's too hard, we can actually do continued pre-training, that's fine. We take a language model that's already pre-trained in some way, and then we can do continued pre-training. But really we want to train the two models together for the language modeling task. Yeah, Siva.
Following up on Sasha's question, is the main problem you think is the embeddings, or you think the actual integration where the LLM doesn't know how to query the retrieval? There are two parts to this equation, right? It's the embeddings is one, and the other one is how can the language model go and fetch the things. So where do you think is the problem?
I think how to read. There are actually also different granularity here. You can do the token level retrieval, you can do the document level retrieval. If you do the document level retrieval, I think it's a pretty reasonable assumption that models can already do pretty well. But another question is like you have to put this back because you want to do end-to-end training, so the model can actually leverage the retrieval better. Yeah.
So these questions of these models will always try to do retrieval, or sometimes they will not do.
Yeah, for this assumption, usually for this family models, we assume that always do the retrieval, but actually in a lot of agentic search framework, you can actually decide to opt out and not to do retrieval. Yeah. Yeah. That's actually another interesting question. So right now my group has been also working on something we call a reasoning intensive retrieval. That for example, for really complex like math coding problems, we assume that they should share some kind of underlying structure. That actually usually helps. If people believe that if I look at this mathematical problem and this can should help solving another problem, and then we put things back in the context, usually it actually helps. But there are also some mixed results. Yeah. Okay, let me move on. I have my big part of the parser. Yeah. Okay, so for the rest of this talk, I want to talk about long context language model. Again, I told you the reason that my group has switched to think about the long context language models. We have made some progress here that I'm excited to share, and I found pretty interesting results. So before I talk about how to train long context language models, I want to first quickly talk about how to evaluate long context language models. I feel like this is something that maybe the community has not fully converged yet. So a lot of prior work in this space has really mainly relied on the perplexity for comparing long context language models. So you probably have seen a lot of the context extension methods, like position extrapolation methods. They usually show this kind of figure. The x-axis is the context context size, and the y-axis is perplexity. They basically show that you can do something that if the perplexity doesn't blow up, then that really means that the model works. They show that this technique works. But in reality, actually, perplexity is really not a good correlation with what people actually care about long context. Sorry? Given a long context, predicting the next part. Yeah. For example, for PG19, the data set has very long context. People evaluate on this kind of held out set. Okay, but the reality is perplexity is actually not very well correlated with the downstream tasks that people care about for long context language models. So there's some nice work basically showing some correlation between perplexity and downstream tasks. And I think this paper is from Sasha's group. So basically, if you see that for serious models, they achieve a similar level of perplexity, they have very different results in this evaluation called ruler. And the people actually don't know people are actually not aware of this reason. Actually, until pretty recently, I came across this iClear 2025 paper. It's a very recent paper called "What's Wrong with Perplexity for Long Context Language Model?" People finally come up with some explanation for why perplexity is actually not good for long context language modeling, because they usually overlook some of the really key tokens that are actually really important for long context processing, because perplexity is always average over all the tokens. And another very popular test for long context language models is actually called needle in haystack. So the idea is very simple. You basically try to insert one needle, multiple needles, in a haystack, which means a lot of the irrelevant text. Then you ask a question about this needle, and then you expect the model to answer give you the answer about this kind of needle after reading through the whole input. So you might have seen figures like this with the green and the red cells. Red means that the model cannot pass this test, and green means it passed when the needles are inserted at different places. But needle in haystack has been very popular. It's very cheap and very easy to run. And I think it's actually a very good sanity check for long context language models development. But I also want to say that at this point, it's pretty clear to me that needle in haystack is actually not very well correlated with the basic real-world task. So this paper, Fu et al. Basically shows that it's actually very easy to quickly saturate performance on the needle in haystack. If you just need to throw in a bunch of long context data, do the fine-tuning for small amount of data, you can actually easily quickly saturate from a lot of red to a lot of green. It's a good sanity check, but we cannot really rely on the needle in haystack to actually develop long context language models. So here, first, we actually decided we need to advocate that we need a holistic downstream evaluation for long context language models. So then my group actually decided to write such a paper, build a benchmark called RALMs. So this paper stands for How to Evaluate Long Context Language Models Effectively and Thoroughly. It's a pretty recent paper, and it will be up here in iClear 2025 next month. So this is a long context language evaluation focusing on downstream tasks. And they support a context length of up to 128,000 tokens. And it covers actually many downstream tasks that people really use for long context language models. And the RAG is actually one of the really core applications that we care about, because people use the long context model for RAG for all these things. But I also mentioned that we are definitely not the first to build a benchmark that actually for long context downstream evals. There has been a lot of popular ones like long bench, infinity bench. But we actually found those those benchmarks usually test models of actually not inadequate context length, or they have all sorts of issues in the evaluation. So feel free to check out our paper if you want to know the comparisons. But the key questions we want to ask when we build this benchmark is, what kind of long context capabilities we actually want to test these models? Needle in haystack is just one kind, recalling the needles. But we also care about the models to be able to read long documents, to actually reason through the entire documents. We care about the RAG application. We care about these models to be actually robust, to actually noisy and irrelevant, noisy and relevant, but incorrect context. And we also hope the model to be able to actually learn the new task on the fly. That's basically the in-context learning. And also the models need to actually have the capability of doing the instruction following to do like complex tasks, such as the citation task I just mentioned. So I will not spend too much time here, but all I want to say is that we put a lot of time creating this benchmark. And this is what actually goes into this benchmark. So we have 7 categories of the task in this long context evaluation. Starting from synthetic recall, it's basically similar to needle in haystack, but we have an actually much more sophisticated version of doing this kind of recall, testing the needle recall. But this really is the kind of like a sanity check, the first test you have to pass for like developing long context models. And we also care a lot about the downstream evaluation. For example, the retrieval-augmented generation I already mentioned. And we have passive re-ranking, and the many short in-context learning, and also some real-world application, for example, long document question answering, long document summarization. And finally, we care about the citation task, attribution task I mentioned at the beginning is basically what we developed like 1 year, 2 years ago called ELK. Just to give you some quick ideas about what's going on here. Again, this is basically the RAG task. It's pretty standard open domain question answering. So we basically like provide a set of documents and ask the model to factoid questions based on this long document, and ask the model to give you the final answer. And for the passive re-ranking, it's basically like a retrieval task that we gave us a model set of the documents and give her like a query. And then we ask the model to basically rank the documents based on the relevance. And then finally, the output should be the ranking of the documents based on these IDs. And then finally, this is like the many short in-context learning. It's like basically like what people usually do in context learning. But only for some of the classification tasks that you actually need a long context to solve this kind of, to be actually able to actually leverage a lot of many short examples in context learning. And also another important thing here is that we don't really use the kind of real world labels like predicting the topic of the document. Instead, we actually have to use some kind of abstract symbols to actually predict this kind of, to predict the class of this document. So the model not able to leverage some prior of these language models. They have to really learn this new task from the context and really to perform such tasks. Okay, so after we build such a benchmark, basically we can make such big plots to compare basically all the frontier models and open-weight models at different input lengths. So you don't have to read through this. We have a lot of tasks and also a lot of models on our website and on the leaderboard. But what I want to emphasize here is, first, for some tasks like a citation and the re-ranking, these tasks are really, really hard for like the open-weight models. Even if you just look at synthetic recall, the open-weight models and the frontier models, they look very similar. But for this task that requires some instruction following, the performance will degrade significantly, especially for the open source models. And we also hope to actually draw some conclusions comparing the different model architectures. A lot of people here care about model architectures. We don't have a lot of conclusions here, but we also test models like Gemba. And we found these models seem to work well, but it's actually really hard to do the apples-to-apples comparison. But at least I hope that this is actually a really reliable benchmark to actually compare the different kinds of long context models. One more thing I want to emphasize is we have 7 categories. We actually found that the models, the correlation between the different categories actually is not that high. That means that the models really require the different capabilities for the different kinds of tasks. All right, okay, so next I'm going to talk about maybe more fun part is actually how to train open source, strong open source long context language models. So I'll first tell you something that actually don't work. There are actually a lot of things that have been already tried in the community. First thing is we found that all these kind of position extrapolation methods with 0 or even minimal training really don't work. People have been keep publishing paper in this space, but saying that you can do some position extrapolation of the rope embeddings. It works because they rely on the perplexity or some other evaluations. If you really look at the basic task I just mentioned, the real-world downstream evaluations, these models really perform very poorly on this downstream task if you don't do any training. And the second fact is, so far I haven't really found the efficient transformers or some kind of modifications to really to break this kind of quadratic attention thing actually really work. We learned this in a bitter way, that we actually have been developing several models and even publishing papers in this space to really make this kind of efficient model architecture, to try to develop this kind of efficient model architecture. And because we rely on needle in stack, rely in perplexity, so we are still able to publish. But if you really consider the evaluation task I just described, these things basically just don't really work as well. So what actually works? A very simple answer is we should do continued pre-training on long context data with full attention. We also don't want to really train the models from scratch because it's just too expensive. We want to develop a long context model that support at least 128,000 tokens. We should do continued pre-training on long context data with full attention. This seems very simple, but there are a lot of design choices we need to think about in this space. So we decided to actually also write another paper with a similar title. It's called How to Train Long Context Language Models Effectively. So in terms of the development space of the long context language models, there are actually a lot of things we need to think about here, including how we should do the continued pre-training, how we should do at least the instruction tuning, the supervised fine-tuning, and how we should actually adjust the transformer architectures to do this kind of long context expansion and the continued pre-training. And finally, there are a lot of design choices need to be decided in terms of how to do the scaling, in terms of number of training tokens, and also the length of the long context language models. And all of these design choices actually have to be guided by the downstream task, like a lot of the downstream tasks that are basically the helmet benchmark that we develop. Okay, so this slide is probably has most information. I will try to go a bit slowly about what we actually figure out like how to develop a long context language model. So this model is called ProLong. It's not a very big model because we are in academia. It's an 8 billion model. By the way, ProLong stands for Princeton Long Context Models, which is a little bit silly. Yeah. Okay, so ProLong essentially is an 8 billion open model that we are actually able to make it support context size of 512,000 context tokens. So what we did here is we definitely cannot train the model from scratch. So we first take the Llama 3 8 billion model. At that time, 3.1 didn't come out. So we decided to do this as quickly as possible to really figure out how to do the long context pre-training. We start from the Llama 3 8 billion model, which only support 8,000 context size. What we did here is we did 2 stages of continued pre-training. The first stage, we tried to increase the context size from 8,000 to 64,000 using 20 billion tokens. The second stage, we try to increase the context length from 64,000 to 512,000 tokens with another 20 billion training tokens. What is actually the training data here? It's actually a mix of high quality, long context, and short context data. So we have 2 stages of training. And this is continued pre-training, so we need to use a lot of raw data. And it's actually a high quality, mix of the high quality long context and the short context data. And where does this high quality long context data come from? We're actually using some naturally occurring the source of data from the basic pre-training corpus. That basically means code and books. We did a lot of regulations in the paper. If you're interested, feel free to check out. But the basic code and books are really 2 really great sources for long context models. But we still need to mix the long context data and the short context data to do this continued pre-training. Okay, so next, in terms of the architecture adjustments, we did 2 things. It's still the transformer architecture, is full attention. So first, we did full attention with cross-document attention masking. That means that if we have like a mix of the long document and short documents we have to pack them together because they are trained together. But we need to make sure that the full attention should be actually masked out, like do not cross a different document boundary. This is actually pretty important. We have some operations starting in the paper. Second thing is actually about this kind of rope embeddings, because we are doing context expansion. So something we figured out very simple is that we just need to simply tune the base, because we need to increase the base frequency of the rope embeddings if you do the context expansion. So basically, we just do some simple tuning of the base frequency for the rope embeddings at the 2 stages of training. Okay. The last stage is actually supervised fine-tuning. Here is something I also found really interesting is we just take some very popular short context instruction data. It's basically ArcherChat to do the supervised fine-tuning. This might not be the best solution, but this is something we figured out it actually works to some extent. Okay, so in terms of results, okay, I hope that I made it clear about how we did this, but I will have some more interesting findings to tell here. So in terms of results, again, we started doing this thing last summer because we were just really curious about how to train long context models. We used trained model with 40 billion tokens. And then Llama 3.1 came out. We found they actually used 800 billion tokens. So we actually only used 5% of their training budget. But as for the downstream evaluation, we actually find that our model is at least as good as the Llama 3.1 across all the categories that we care about. So we must have done something correctly, at least in terms of data and in terms of our training recipe. Okay, so again, we just use 40 billion tokens. It's something really just 2 students pull out this effort. But I want to tell you something we learned in this project that I found super interesting. That also I know there are a lot of theories here that maybe is actually some findings for you to actually think about, like after this talk, to really figure out why this phenomenon actually happens. Okay, so the first finding is I already mentioned is you cannot just use the long context data. You have to mix the long context data and short context data together. If you just train on the long context data, it definitely hurts the performance on the short context task. But it actually even counterintuitive is it actually also hurts performance on the long context task. So here's some like XS here is basically the percentage long context data. Basically, you use like a if it here is basically like if you use 6% of long context data and 40% short context data. But what's really interesting to us is you actually, if you don't use any if you use like 100% of long context data, you still hurt the performance on the long context task a lot. But if you use more of the long context data, you definitely like this is a short context task. That definitely the performance decrease. Yeah, Sanjay.
So is it kind of binary, like all long tasks are roughly the same length, or is there like a distribution on length?
No. Okay, so we take the data, the long context data that at least 512 tokens. Then we just truncate and drop the rest.
500. No,
for example, if we scale up to 64,000 tokens.
So I'm not sure, like a long task fills the entire context, or is it still only a part of the context?
Oh, the long context data fills it. Because, for example, if the context size is 64,000, that means that we only take the long context data of 64,000.
Yes.
And we also have the short context data. That means that we are going to pack those short context data in the different batches.
No, understood. But like, all short context data are roughly about the same length, and all the long ones are roughly the same length.
So all the long context data are definitely the same length.
It fills completely.
Yes. We truncate at the end. It has to be at least that context length.
At least that.
Yeah. When we truncate and drop the rest. Go ahead.
Was the 60/40 based on some heuristics, or was it?
It's based on these 2 figures. We figure out that, okay, you have to do 60% to achieve the really good trade-off between both long context task and short context task.
And do you have like some intuition, is it related to the model size also? Or is it related to multiple stages? You're doing like stage 1, 64K, and then 512K later on?
I believe that we have similar findings for both stages. We didn't do really a lot of ablations on the model sizes because this is just too expensive. Yeah.
Do you control for the domain of the data? Because if you have only the long context data, you also have a very...
Exactly that's the point. So the long context data only comes from those 2 domains. But the short context data can come from all different domains in the pre-training data.
The problem was domain.
Yeah, it could be that means that if you only use the long context data, it gives you a very different distribution of the pre-training data. Yes. Another thing I found also interesting is we also did a lot of ablations in the paper in terms of quality of long context and short context data. We actually found the quality of both long context data and short context data matter a lot. Even the quality of short context data can actually give you a much better model in terms of long context task performance. So we have like very significant differences in the paper. Yeah.
How did you quantify quality?
No, this is all about the downstream evaluations, long context downstream evaluations, and short text evaluations. Yeah, we don't have like a notion of the quality. It's really like we applied on like many different combinations of the data engineering and check the downstream task performance. The higher the performance, we believe the data is better. Yeah.
Just to get a perspective, how much is 64K tokens? Is it like a research paper of 8 pages or?
Yeah, I have a slide about this. Yeah, the GPT-3 paper. Where I show this? Yeah, I can show this. Good. I skipped this slide. Yeah. Okay, so yeah, you can see the GPT-3 paper is like 75,000 tokens. Yeah, and for the code, it's like 10 million tokens. Sorry, maybe I should have skipped this slide.
So like, I was wondering, if I give a person or anyone the lost, let's say 10,000 tokens, 20,000 tokens, would that be enough to predict the next word? So like, in the end, you're doing next word prediction, right?
Yeah.
Most language modeling is very local phenomena, right?
Yeah, that's the point. That most tokens you don't need a long context. But if you have really naturally occurring data like a paper, research paper, or code, there's definitely still a few key tokens that actually really need some context to help prediction. That always really plays an important role in the final evaluation. I want to continue and finish this part as soon as, yeah. Okay, so I have 3 findings in this part. The second finding I also find it really interesting is we did 2 stages of training. The first stage we train on 64,000. Second stage we train on 512,000. But the evaluation is only on 64,000, and we did a control study. We just continue training on another 4 billion of 64,000 training versus continue training on 4,000 of 512,000 context length training. We control the total number of training tokens, so the number of documents are different. It's actually surprising that if you train on like longer context, like 512, it still helps improve the performance at 64,000 context length. This is something we have some like intuition about why this happens, but I actually find it really interesting to think about. We actually need really long documents to actually even work better for the shorter context. Sorry, this is wrong. Okay, the third thing I want to talk about is actually this instruction tuning. Again, what we did here is continue pre-training on the mix of the long and the short data. And then we just did a supervised fine-tuning on the short instruction data, UltraChat. We found this model actually performs reasonably well in terms of instruction following. If you do not do this instruction following, this model basically cannot do anything in terms of, like, for example, long document summarization or long document question answering. Sorry, at least the citation task. Question answering, I'm not sure. But summarization, you really need some kind of instruction following. But it actually works pretty well. In the paper, we tried a lot of things about how to really generate long context instruction data. But this still, so I think it's still open question that the community has not figured out how to really obtain the high quality long instruction data. But still, I found it interesting that if you just do the supervised fine-tuning on the short data, it still works pretty well. Okay, so how many minutes I have? Like, I think I start 5 minutes. Yeah. Oh, okay, sounds good. Okay, so I will just use the remaining 2 minutes to talk about another really recent interest from my lab is we are thinking about like shifting the long context language model research from the long input task to long output task. So far, for the task I described, really focus on like you need to read a very long input. But recently the reasoning model came out. We really need to think about how to make these long context models actually work for the long output task. I'm not going to have time to talk about this paper. She's actually here as well, so you can talk with him. So we actually wrote this paper called LongProc, benchmarking long context language models for all long procedure generation. Basically, we present another framework to just try to test this kind of structured long form generation of the long context language models. And these models, really interesting thing here is that we really require the model to follow like a very detailed specific procedure to actually generate this long structure output. But also the output is actually deterministic. So it's actually, you have actually a very reliable evaluation. So it's actually a really big challenge in long form generation. For most of the tasks, you actually require long form generation. You don't have a really good way to evaluate this. But we actually, by design, we actually have a good ways to evaluate this. So one simple task is, for example, you have an HTML page, and then you try to extract some like genre, a year, and the rate of movie to generate like a TSV file for this kind of long form output. Or you can do some kind of like a really reasoning like models, for example, follow a procedure and do some kind of search. So this is one of the tasks. I'm not going to talk about this. Just finally, I just want to talk about some of the results that we are very interested in. First, the frontier models that are actually capable of handling, let's say, 128,000 context tokens. It's actually do very bad in this kind of long output task. They actually fail, even the Gemini Pro model, the 1.5 Pro model. Actually, they fail at 8,000 count output lengths. The reasoning model is actually pretty good compared to the instruction tuning model counterpart on this task. We actually think that the reasoning training can do something with the long context abilities. I'm not going to talk about this, but also we found something also interesting is that reasoning models can do pretty well on this task. But if you give the model some kind of procedure, the models can do better. But for the instruction tuning models, if you don't give the model any procedure, the models cannot do any of this. Yeah. So why? For example, for countdown, it's like you need to give a bunch of numbers. You need to come up with the arithmetic operations. So we come up with this procedure to do the basic DFS, to really figure out the procedure to figure out what should be the correct answer. So the model needs to follow this procedure and finally find the search solution. So this is something very similar to the long chain of thought that people have been seeing in the training models. But for this task, we define the model has to follow this very specific search procedure to do this task. So the output needs to be very long and to finally arrive at the answer. OK, so I think these are a lot of interesting things we can talk about. Feel free to check out the paper. And yeah, I think I'm done. And yeah, I talk a lot today. So I believe that a lot of progress has been made in long context models. They are super useful for RAG. And I think the research focus will be shifting from long input to long output very soon in the space of long context language models. But the progress in the training retrieval-augmented language models hasn't been really made much. But I still hope to see more breakthroughs in the future of language models. OK, I'm going to stop here. Thanks for joining me. Yeah.
But why should I expect that to be the case? Intuitively, it feels like long context isn't fundamentally different.
So you are questioning why we care about long context models, or why this kind of minimal training doesn't work?
Why should we expect that the minimal training procedure should work in that?
Yeah, I agree. So that's why I'm actually surprised when I see a lot of claims that okay, if you just do the minimum changes, it can actually work. It's actually not the case. But people, there are actually a lot of things interesting to think about this kind of positional embeddings. So people have been thinking about how to tune those things. I agree with you that these things actually don't work. Yeah, that's why we are trying to question this. Yeah.
Yeah, I'm still trying to understand your thoughts on why retrieval-augmented language models fail, where these long context language models are succeeding. So what is the
I would say they are very different things in terms of the training paradigm. But it just happens that it's easier to figure out the solution for training the long context language models right now. And the retrieval, because the database really has a lot of, is very large. There are a lot of engineering efforts and also the technical challenges that we actually haven't really fully figured out yet.
So it's not as simple as this long context?
I would say long context language model is easier to task to solve at this point. Yeah.
OK, so maybe we should transfer over the computers and thank Danqi for the amazing talk. Also your microphone, too.